Hello, how's everyone? Wait for Jesse if he's coming. Good morning. Morning. There he is. Okay, so welcome to the meeting. Yeah, just getting started. So yes, I hope everyone had a good week. We had 2 meetings this week, or actually 1 meeting this week. I had a meeting with Shubham about GSOC project. Yeah, so we had our cybernetics meeting this week, which there was a little variation on the time, little wrinkle in the timing, but I think we had a good discussion about a paper that Jesse discovered on natural, sort of the natural world versus the computational world. So that was a good discussion. And we didn't have a Diva Worm meeting this week. We decided to forego that in lieu of a conference at Genalia that I attended. And I think Morgan also attended. And this was on 4D cellular physiology, so 4-dimensional cellular physiology. So that's 3 dimensions of space and 1 time. And people had, there were a lot of good talks there, engaging with, of course, AI and the latest biological analysis techniques. And yeah, it was good. I don't know if anyone had any updates they wanted to share. If you do, go ahead. No updates from Amanda.
I guess my general are it was really interesting to have one meeting. I had to cancel Cognition Futures this week because of a bunch of stuff, and it's sort of I'm getting into my finals period, and really there's a bunch of things going on, but it's been an interesting week. It's a little bit of a difficult week, but it's an exciting time because the seasons are changing here, and sort of literally and metaphorically also. Like we're closer to the summer. We have the Embodied Intelligence Conference. Like kind of things are starting to go into the actual active part of the year. It's been interesting to think about the embodied intelligence submissions that we have. And broadly, a lot of work is being done on some of the administrative side of things, and I'm very interested in sort of improving some of the structure and functioning of a bunch of stuff going on, both like Himnshu Futures and things in the lab. There's certain help I'd like to get for some administrative things and everything else. And also we didn't really have time to get to it. It's been a bit on pause for me too. That's why I haven't brought it up. But we have had some help with some of our onboarding materials and training. Jen's done a lot of good things with that. With lab, with thinking about procedures for ethical summer code, similar things with JoPro, and some of the other programs I'm helping with. So that's been really nice and really good. One week, or I would like to have more of a presentation on that. It won't be this week. It's been a tighter week on that for me. My major focus right now is on a bunch of this writing. I have a lot of things that just write or draft. That's what I really want to do the rest of today. Sort of just get time to do that outside of the other urgent things that are going on. And yeah, specifically the Thursday meeting, it was kind of a double shot because we had Amanda had to do it early, and then Bradley showed up at the normal time, so we reviewed things again. So it was sort of an interesting. I can imagine this the closest thing I've had to when a teacher you're teaching back-to-back classes, and you just like we're just like it's back-to-back panels that are the same panel,
Yeah.
and you have different discussion about the same material back-to-back. So it's kind of interesting, and I think I'm excited to next time bring that together. There were three very interesting things that um, project-wise came from that. One of them was Amanda's focus on memory and kind of relation to the Cognition Futures project, or just like in general, and discussion about memory. Um, we've had a number of looking at physical memory and topics about memory. And if Amanda wants to talk about interest in memory, I encourage her to do so. But I will dovetail into it led to a really interesting path for me having to do with um, memory as a space or a medium that's related to agency and also essentially trauma or the I would say experiences that shape an agent's have a major impact on an agent's sense of self and certain abilities. Um, and I've found a few things in that space which I'm absolutely interested in pursuing more. I found an article. I think I don't know if I put it somewhere or not, but let me see if I can just yeah. I'll really briefly share my screen just to show this. And I'm not going to go through it in a particular sense, but just because it's here. Um, this article and other work in this space looks really interesting, in part because there's an embodiment component that has to do with some of our friends that we well. There's a reference to like Maurice Merleau-Ponty. I'm a little bit less familiar with Sean Gallagher. I forget if we mentioned here or not before. But then Catherine Malibu is sort of related to um, Derrida and other sort of people in a critical space, and that's I think this is also the person who I think this is the body keeps the score person or something like that. Yeah, okay. So this article is is um, nice, but it brought me back around to uh, Malibu's takes on plasticity, which are interesting, and the sort of philosophical takes and some biologically inspired things too. Um, and I've kind of been looking a bit at, like at what all of them are about. So that was a really interesting um, project core that I really want to work on, and it has ties to the DSM project that we mentioned and ties to some other things. So that was one of them. The second one was Bradley brought up this idea. It's like, hey, wouldn't it be? And it's like, wouldn't it be fun or be interesting to think about emergence and computation and sort of how they're related or squared and how people are talking about them. And it fits nicely in sort of the um, we had the paper a while ago about the different kinds of intelligences, and I'm doing a lot of work on sort of, I guess, taxonomy and terminology and language and things like that. So all of that's relevant on my mind. And yeah, I think emergence and computation, particularly for this lab and also DORMR, like these sort of major concepts that we talk about all the time. And I really appreciate. I think Bradley's really good at sort of articulately picking apart what people are trying to do with the terms in the scientific or the philosophical work they're doing about the theories, whatever the fields are. So yeah, I think there's something to do there, and I think it does fit. That was brought up in the cybernetics reading group, but I mean it cuts across a lot of the stuff that we're doing at that sort of the concepts that we think about a lot. The lab tend to bump up against that quite a bit, whether it's in like this like computational psychiatry stuff, whether it's in cybernetics, whether it's in a lot of the developmental stuff, developmental AI, or all these things about computation. The paper that the paper was by Yogi Johannes as the lead author, and he kind of drew this very hard line between the computationalists or the pan-computationalist people and the emergent, I forget whatever it was called, the people who weren't that way and saw, had a different view on computation and cognition and how agency relates to that. And I don't know, I'm not going to get into that right now. You can for the meeting or whatever, but I think that's definitely a project I'm interested in trying to develop about looking more at emergence and computation. And I guess the third item kind of spills over already in the memory thing that I talked about with my own interests. And then there's some other things I need to follow up with that Morgan mentioned for like neurotech stuff. So those are kind of the broad three categories I'll say that came from the Double Shot Tuesday, which was unexpected but fun, or Double Shot Thursday, which was unexpected but a lot came from it, so that was nice. And that'll be my update for now.
Yeah, it's great, Jesse. Thank you. Yeah, there's a lot to follow up on. And a lot of what we're doing with Cybernetics Reading Group and Cognition Futures Reading Group. Welcome, Sarrah and Shubham. I know Sarrah and Shubham are just in GSOC.
Hi.
Hi.
Yes. Hi, everyone. I had my exams this week, so I didn't have much in terms of updates. I did find an interesting paper. I'll send the link in the chat, which talked about kind of trying to model open source software ecosystems in particular. And they also it suggests a lot of like trying to use data from the real world techniques like the IRC, etc., that we discussed. So I think I'll try to like read that more and see how we can sort of use that in our project. But yeah, that's it from my side.
That's great. Thank you. Yeah, so I met with Shubham yesterday. We talked about GSOC things. And so, yeah, this, the open source project is, we talked a little bit about how you might approach that. And so we have open source repositories for that. We have a paper as well in ResearchGate. And so I think I've linked to that in the project description. But there's a paper that we did, or we got together on the open source sustainability project for the last 2 years. We've been working on it. And, there are the three models. There's the sort of the web interface, and there's the vision for it. And one of the things we do in this project is to try to kind of figure out how to measure open source sustainability. So we approach sustainability as basically those things that help the project, stick around, because a lot of projects will fail or they'll be dysfunctional, and it's something you can't necessarily avoid. So you have to have measures of things. You have to be able to assess things in order to say whether something is sustainable, whether it's not sustainable, and so forth. And so we talked a little bit about, and I think in Sarah's talk last time, kind of coming from out of that, we got the sense that we need to have good measurements of sustainability, or at least of what people are doing in an open source community, to see how those things can be optimized or improved, or whatever. So we have some existing measures in some of our models. If you go to the reinforcement learning model in particular, you'll see that there are a number of measurements that are used, the parameters where the values can be set. and you can run the simulation with those values. And we can get those values from things like GitHub repositories or Slack and Discord channels, but we that's why we have the APIs that we have. Like I said, the GitHub API can sometimes provide information about that, where we can just simply model what we think sustainable community and non-sustainable community look like. So there are different ways you can measure sustainability. And of course, GitHub repositories are not the only place where community activity happens. So a lot of times you have communities where there's a strong educational component, or there's a strong participatory component that doesn't involve GitHub repositories or code. And so, if we can kind of characterize what those are, we can make, create estimators. We can, maybe get data from other sources and kind of hand code them into values that make sense. So we know kind of what the range of values are for something. So there are a lot of ways we can collect data. There are a lot of ways that we can create these variables and quantify the things that we need to quantify. Now, in the reinforcement learning model, we also have this model of participation. And so you might see reference to like an Earth shot, a moon shot, and a Mars-Jupiter shot. And those are just the levels of sort of project complexity, or sort of the number of things that need to happen in order for a certain project to succeed. So, for example, an Earth shot might be like fixing a bug in the code, or it might be like, reviewing some code or reviewing a document. It's very simple. It's very easy to make that contribution, and it's easy to sustain, because if someone does a series of those things, they're contributing over time. Their contribution is stable, but at the end of the day, it's not contributing to this larger scale goal. So we have an Earth shot, which is essentially sort of the very pedestrian things that you do in a community. Then you have the moonshot, which is, working towards a project goal. You have a lot of moving parts. You're trying to realize those things. You might have multiple people contributing to a pull request, for example, and you get that out. And you have to coordinate people's efforts. You have a lot of things you need to make sure they're in place, and so forth. So that's a different level of sort of competency in the community. If the community is dysfunctional, you can't necessarily pull something like that off, even if you can pull off the Earth shots. And then the Mars-Jupiter shots are those things that are sort of open-ended, that don't really have a goal in mind. So a lot of projects will start off and, you try to plan them, and the plans go awry and you have to adjust things. Or sometimes you don't have the endpoint in sights when you start the project, and you have to kind of produce things in multiple stages. So the idea of a Mars-Jupiter shot is you're, going from planet to planet. You're hopping and trying to get to an end destination, and it isn't necessarily linear. So that's the idea. So, we think about this in two ways. We can think about this in terms of variables, or in terms of these frameworks for project complexity. And so that's going to be key to some of the simulations. And, if we're talking about any simulation, large language models, reinforcement learning, active inference, or whatever. So it was very good last week, Sarah's talk on LLMs. There's a lot of stuff there. If you weren't at the meeting, you can go back to the recording. I encourage people to go back to the recording to sort of get the sense of what the proposal was. And I'm sure Sarah will work on the proposal. And then Shubham, I encourage you to, Himnshu, encourage you to go into the, code, go into the concepts, and give a presentation on it as soon as you can, because I think it would be good to, I think the presentation would help clarify some things for you, going through that process of putting together a presentation. And so I think that's great. Okay, so hello, Himnshu. I know that Shubham wanted to talk to you, but yeah, I think he's logging back in, so it's fine. But welcome. Let's see. We had some activity in the chat here. So this is the paper that Sarrah put in, Open Source Software Ecosystems Towards a Modeling Framework. Then Amanda said, regarding the cybernetics research discussion group, I made a notion for the mission statement that could use some filling in. So this is the mission statement that Amanda created in the notion. Okay, I'm looking at it. So the mission statement is basically kind of goals for the cybernetics reading group. Yeah, so it looks like that's what that is. And so yeah, we have like a number of themes. We talk about like papers from week to week. So those papers have a lot of content in them. And, if you read them in isolation, serially, you can kind of take notes on major themes and how they link together. In our group, we, talk about them a lot. So a lot of things emerge from those conversations that are added value. So that's where that's going to live. Okay, so Jess is going to look at it later today. And then Shubham said, sure, I can give a presentation next week. That's great. Thank you, Shubham. This is the paper I was talking about on ResearchGate. And this is kind of continually updated. So we have the contributions from the last 2 years on the open source sustainability project. This is open source community sustainability using agent-based models. And this is, all the people who have worked on this in GSOC. Actually, I haven't updated it for last year, but I'll be doing that soon. And then, it basically describes the project. It describes some of the models. It describes a number of things here, that it's basically an auditing tool. So if you're familiar with sort of auditing of AI systems or auditing of automation, it's a very similar thing. You're auditing, in this case, an open source community. And so we're using data analysis of metrics from specific platforms, so there are a number of platforms that exist that do this for communities where they, come up and they can put in their metrics and they can give them some information about, how to improve their project. What we're doing in this project is we're running simulations to sort of give alternative scenarios for projects. So if you give us your parameters, ideally, if you give us your parameters of your community, if you can define those parameters, and there's going to be a lot of variation from project to project and what those look like. But if you can characterize those and you can plug them into the simulation, you can get different alternate scenarios of how your community might turn out. So that's what we're trying to do, and that's what sort of the power of simulation is, to provide those alternative scenarios. So this kind of goes. If you read through this paper, you'll get a sense of what exists out there right now, what kinds of things we have in the project, what we've worked on, and then kind of the vision for the future, and then where your proposal would fit in. Okay, so all right, yeah. So Himnshu says, anyone interested, feel free to reach out to me in Slack, direct message. Okay. All right, so that looks good. I don't know, Morgan, or did you want to give your update now, or did you want to wait? Yeah, Himnshu says that the paper is a great first step and would help directly focusing your efforts instead of, kind of figuring out where things stand. with the project. I wanted to talk about two events. One event being the upcoming conference, and the other being something that happened this week. The first thing is the Embodied Intelligence Conference, and that's happening this coming week. So this is happening this week from Wednesday to Friday, I believe. Yeah. So the Embodied Intelligence Conference, it's happening from March 20 to March 22. So this is the website here, embodied-intelligence.org. And this is the program that they have up on the website. So this is the conference program. As we talked about a while back, there are a lot of interesting talks, a lot of diversity in the talks. You have people like Neil Shubin, who's a paleontologist. You have, people doing embodied robotics. You have people doing, embodied sort of human embodiment. People doing complexity theory, people doing different types of neuro-inspired AI is the best way to put it, and other, projects and sources of expertise. So I'm really looking forward to doing this. This is sort of based in England, Greenwich Mean Time. So these 9 o'clock Greenwich Mean Time for North America is pretty early. So I think they're going to record all the sessions. So that's good that they'll have that summary. But there are also breakout sessions, and that's where our group comes in. So the breakout sessions are sort of, it's I think noon. They're all noon Greenwich time. So like if you, in that North America, that's, it's 5:30 Greenwich time, or 5 o'clock, something like that. So it starts 5 o'clock Greenwich time. So that's noon my time, 1 o'clock Eastern. Check the web for the conversion for your time zone. But basically, we're going to be presenting 3 things during these breakout sessions. So the breakout sessions are really nice. I've done this before, where you have a bunch of people, and there's a lot more diversity even than the main schedule. So there are a number of topical areas, a number of topical foci, from morphological computation to bio-inspired cybernetics, self-organized systems, functional materials and designs, AI-based perception, human-centered systems, computational approaches, cyber-physical systems, life with machines, applied cognitive psychology, and that's all of the topics, it's quite diverse right there. So we have 3 talks happening. So the first one is in this computational approaches section. Now it looks like Jesse is up in that group of people with his topic, diverse intelligences and diverse terminology, considerations on common language and models. So, again, this is like a 15-minute talk. It doesn't get deeply into any one thing, but, they're very interesting in terms of the diversity of topics. I am in the self-organized systems track, and that is this talk on developmental neurosimulation is a route to embodied morphogenetic inspired intelligence. So that is basically an update on our efforts at our what we call developmental AI in-house, but is also known as developmental neurosimulation, which we've written a number of papers on using Bradenberg vehicles as model systems, but also other types of agent-based systems as well. So this is actually related to the GSOC project on agent-based modeling. So when you think about agent-based modeling, you can think about the paper that I talked about with respect to open source sustainability, but also we have these other agent-based models that we work with. And, we of course work with the Bradenberg vehicle. We work with developmental Bradenberg vehicles, which is where the Bradenberg vehicles have this developmental stage. we have other models that we're interested in. And so being able to train those in an environment like something like maybe AI Gym, or benchmarking them in some way, or figuring out unconventional ways to handle the computing in those agents. That would be a goal, I think, for the lab. And so I'm going to talk about that. Actually, I'm getting ready to give a recording, and I'll talk about that in a minute, and put that on the YouTube channel. So you don't have to be in the session to get that talk and to see what we're doing. Then the final one is Hussein Ather, who is a member of the lab who's interested in virtual reality and cognition and philosophy. And he's giving a talk on navigating reality, exploring spatial cognition, virtual environments, and philosophical implications. So basically on spatial cognition and VR, which is a classic area. And of course, we have our VR project as well for GSOC. So he's going to explore a number of topics on this in his talks. So in the general channel, I posted an announcement for this. This is where I announced the 3 breakout session talks. And I would like for Jesse and Hussein to record their talks and get those recordings to me so I can put them on the YouTube channel. We've done this in the past, and I think it's good because, as far as I know, they're not recording the breakout rooms, which is kind of a shame because I think those are great sort of sessions. It's more informal than the regular conference, and there are a lot of really interesting things going on there. But I would like, if you can, to record them and send me a recording. I can put it on the YouTube channel, and we'll get a lot of views of people who didn't attend the conference, people who want to go over the talk a number of times, et cetera, et cetera. So that's something that'll be worked on. So I think Hussein and my talk is on Wednesday, and that's at the 5 o'clock GMT in that slot. And I think Jesse's is on Thursday, so day 2. And that's going to be at the same time, but on Thursday. Well, good luck to everyone there who's giving a talk. And you can register for that if you want to view it online. You can go through the website, go through the link, and check it out. Second thing I want to talk about is the Neureality Hackathon. And so this is something that Hussein, who I just mentioned, attended I think it was last week at this time. So he wasn't in the meeting last week. He was doing this event. And so this is, again, this VR track that we have for GSOC. And we have this hackathon that happened last week. And they're doing a lot of things with like brain-computer interfaces with VR, other kinds of things. So they had different hacking tracks, their vision, a schedule, and their sponsors. So let's look at the vision for this. So the vision is basically threefold. So the first here is hands-on experience. So this is the first of its kind hackathon that offers practical hands-on experience with both neurotech and VR/AR technologies. So it's like, there's not a lot of opportunities to get your hands dirty with some of these new technologies that are coming out in that space. And, you have a group of people who are likewise interested in building things with them. So that's the hands-on experience part. Participants create impactful projects with cutting-edge gadgets, enhancing their skills and contributing to their professional portfolios. So this is where you have a project that you can see through. And what I understand that, they did a pretty good job of that in Hussein's group. There's a professional development aspect. Neureality is a platform for students to explore their passion in the neurotech and VR/AR industries. So this is the professional development aspect. So, this is something that's, of course, very important as well, making connections with people, but also learning about the topic. Through keynotes, workshops, and mentorship, we foster a community of learning and collaboration, connecting participants with peers, future startup co-founders, and seasoned veterans in the field. So it's always a matter of like kind of knowing people, or, getting a sense of where the opportunities are, also connecting with people, collaborating, and learning the cutting edge stuff. And then building for the future. Your ideas and projects shape the future of our relationship with tech. So it isn't just about the platforms that come out or the coding languages or whatever. It's the vision and sort of the projects that emerge. So projects have to be sort of viable in terms of their structure and being able to be put into practice, as well as the people around it being able to see it through. So those are all aspects of open source sustainability as well. Participants create new applications and solutions that can transform the way we interact with the digital and physical worlds. Our goal is to cultivate a forward-thinking mindset where the boundaries of what's possible are constantly pushed forward. So that's what the vision is. The hacking tracks. This is, I guess they have a couple listed here. There's work with G-Tech Unicorn EEG. So this is an EEG platform, and this is a specific technology. I guess G-Tech Unicorn. So these are the interfaces here, and they want to build what they call neuro games. This interface using Unity and this interface that records things in the brain as you do this. So it's this sort of naturalistic cognition aspect, and so they really want people who can develop content around this. But it takes a lot of different skill sets to do this and to try to figure out how to build applications. The second is using Physiolabs to build VCIs. So this Physiolab XR this is actually recorded, so you can go to this and look at it. This was based on this Physiolab XR toolbox, which is a Python-based application designed for visualizing, recording, and processing data streams, including making predictions. So this is basically for these sort of interaction interfaces like BCIs or other types of experiments that you might run in a setting. So if you want to be able to look at brain activity under different conditions, you can do it with this toolbox as well. So this kind of talks about the Physiolab XR platform and how it enables construction of BCIs. So this is this real-time closed-loop BCI system platform. So that's what they're building towards. The closed-loop BCI system is where you interact with, say, like a virtual environment or a video game, and you're recording the brain as you do that. And so you, as the person who's interacting with that medium, you're doing things in response to the medium, but you're recording brain activity, which then gives you the cognitive state, and you can actually see shifts in the cognitive state over time. So this is the closed loop aspect. So this has been like a goal for many groups for many years. People have tried to build them, and so the technology is out there. People know kind of how to do it, but making it really good and having really compelling experiences where the recording device doesn't get in the way of that is another kind of goal that we haven't really realized yet. So there are a lot of things that can be sort of approached in this space, a lot of things that can be improved upon. And so this is something, I guess, where they had a number of different groups working on. So this was all the Columbia University in New York City. And I know that Hussein was talking about this in the Slack quite a bit. He's very enthusiastic. Here he is, Hussein Aether, and he's a hacker. That's his label. And he has some people there he met. and they formed a team. I'll talk about that project in a minute. Of course, this is the sort of the intro to the hackathon. So you always have sort of an intro, and you go through what you're going to be doing, and then you break off into groups and you start working on a project. So okay, so this is a project, Electric Sheep, and this is actually featured on devpost.com. And so this is called Electric Sheep. This is typing is slow and boring and hard, and it's not accessible to many people. What if there's no physical barrier between your mind and the computer? What if you could type with your mind? So the idea is you have this interface where you have this keyboard. Usually you use your fingers. If you're in VR, sometimes you have to use the controller. Or if you're on the Apple Vision Pro, you might use your fingers. You can do this with the Meta Quest 3 as well. You pinch, and you have to hit these keys that really don't give you any physical feedback. So it's really weird. You can also use eye tracking, but that can be similarly a problem because the resolution isn't very good. I mean, sometimes you'll mistype or something like that. So, the technology, we talked about this a while, I think last summer. I did a number of topics in VR, and one of those was, inventing a keyboard that provides physical feedback to the fingers as you type. So you've hit a button, or you've hit the right button. And so that's always been a problem with these kind of virtual keyboards. This is an example of where you have the keyboard on screen here, and then instead of using your fingers or even eye tracking, you're using, you're thinking about a letter, and that thought has a signal, sort of an electrophysiological signal that can be segmented out and then translated into an action. So if I'm thinking about the word awful, AWFUL, I can think about that word, or I can think about the letters of that word. And there's some signal in the brain that corresponds with letters or words that can then be translated into key presses. So that's what they're trying to do here. So, this is basically the inspiration is actually from people who have mobility limitations. So you could do this, anyone could do this. It's actually maybe useful to anyone, but especially people with mobility limitations. The idea is to create a tool that allows users to convey their thoughts effortlessly and without physical constraints. There's something called Cortex Type, which facilitates typing through mind control, harnessing brain-computer interface technology to translate thoughts into text. The integrated EEG technology with advanced algorithms to interpret brain signals, particularly the positive going response at 300 milliseconds, creating a thought-to-text conversion process. So this is the platform that they're using on this project, and they're trying to develop for it, develop different types of content in different parts of this. So what we learned, it takes time to set up all software and hardware correctly, so we need to start earlier next time. And the EEG signal is very noisy. We might need to consider some cool denoising techniques. Basically, time management, or knowing the scope of the problem, and then knowing the technical challenges. And that's typical of a hackathon, but that's why we have hackathons, so we can at least lay out the problems and work on development and all those things. So this is built with Oculus, Python, and Unity. And they have a GitHub repository, which is here. So this is for Cortex Type, and this is all open source. So Hussein liked this, and the Katerina, I think, is one of the developers. Says leave feedback in the comments. So they're really doing a lot of things with this Electric Sheep.
It's important to say that it's not trying to use your language center.
Right.
That it's doing your kind of it's sort of a surprise detector, and putting up letters until you you're like, ooh, that's the letter, and it's picking up the ooh signal. You know, as opposed to mind reading.
Yeah.
Or you know, trying to capture the like an internal speech stream or something like that. Some, I mean, so they said P300s, and then there are others that use the SSVEP, where they'll have the letters flickering at different frequencies, and you can literally choose by your eye gaze which letter to look at, and then the signal detection is just focused on picking out the frequency. So, you know, these are great assistive technologies, though.
Yeah.
Right. Yeah.
Right.
But yeah, hackathons are always too short.
Yeah.
like you know, it's 2-day hackathon, so you should do like a week's prep. Yeah.
So this is artificial intelligence brings a virtual fly to life. So it tells you that there was an event at Genelia on 4D cellular physiology, and so Genelia is a research campus near Washington, D.C. It's run by the Howard Hughes Medical Institute, and they have this place called Genelia Farm, which is this huge research campus where they do all sorts of biomedical research. So this is, you know, some of it is like, you know, wet lab stuff. Some of it is dry lab stuff. This is an example of something that is, it was developed by Genelia scientists and Google DeepMind scientists. So DeepMind, of course, are doing AI research. Genelia is where they have knowledge of the fruit fly and its physiology and its connectome and all these things. So this is, I'm not going to show the video here, but this video shows the fly model reproducing a flight maneuver, or it does what they call spontaneous tuning. So the fly has a brain. That brain, we have characterized different parts of the connectome having to do with like sensory inputs and motor control and things like that. So they know like the connectome and what it looks like. But the question is, how do you translate those signals in the connectome, those connections, to behaviors in a fly? So it's almost like an embodied cognition question. If a fly is producing a certain connectome output, how does that map to behavior, and more importantly, behavioral regulation? So the fly just doesn't like turn on its motion and turn off its motion. It has different motion behaviors. Sometimes they have to hover. Sometimes they have to, you know, initiate flight. And so there are a lot of things that are happening. Sometimes they have to turn left and right. So there are a lot of things that have to happen during flight. And so this video shows the fly model reproducing a flight maneuver, which is what they call spontaneous tuning of a real fly, executing commands to walk at a speed of 2 centimeters per second. So it walks on a surface, and then it's trying to figure out sort of the direction it should go. So they not only fly, but they also walk on surfaces. I think you've seen this with houseflies. They'll walk on a surface and then start flying, and they're always trying to assess where they are in space. And so this is what they're doing. So they're turning left and right, and the model imitating a walking trajectory of the real-life fruit fly, which includes walking at different speeds, turning and briefly stopping. So this is where the fly is walking on a surface. It turns and stops. This is, I don't think this is the fruit fly, it's a housefly. But they're using the stuff that we know about fruit flies. Or actually, I think it is a fruit fly. You know, by infusing a virtual fruit fly with artificial intelligence, Genelia and Google DeepMind scientists have created a computerized insect that could walk and fly just like the real thing. The new virtual fly, which they have this paper on bioRxiv. And so this is the paper, whole body simulation of realistic fruit fly locomotion with deep reinforcement learning. So they're using deep reinforcement learning, hence the people from Google DeepMind, and they're applying this to the problem. So this is, I'll read the abstract of this. The body of an animal determines how the nervous system produces behavior. Therefore, detailed modeling of neural control of sensory motor behavior requires a detailed model of the body. Here we contribute an anatomically detailed biomechanical whole body model of the fruit fly Drosophila melanogaster, which is the typical model system in the Mujoko physics engine. So Mujoko is just a common physics engine that we can use to simulate things. Our model is general purpose, enabling the simulation of diverse flight behaviors, both on land and in the air. So this is where they show in the video this walking behavior, but they can also model flight as well, or at least they want to. We demonstrate the generality of our model by simulating realistic locomotion, both flight and walking. To support these behaviors, we have extended Mujoko with phenomenological models of fluid forces and adhesion forces. So this is where you take the model of the connectome, there's an output to some embodied model, and then you have models of fluids and adhesion, so things in the environment and how those things behave. So, you want to have, for example, simulate like liquid or simulate the air, and it has different levels of resistance. So sometimes the air is more resistive or less resistive, maybe depending on the humidity. If you have like a liquid, it's more viscous or less viscous, and you can define those parameters. And so the movement behavior is going to vary with that. And so you can, as well as adhesion. Is the surface really sticky, or is the surface really not sticky? And so you can do this with physical parameters that you can set the value of. And like our agent-based models, you can simulate that over time. You can just run the simulation with those values, and it gives you alternate scenarios. Through data-driven end-to-end reinforcement learning, so they're actually putting data in and they're doing this end-to-end reinforcement learning, we demonstrate that these advances enable the training of neural network controllers capable of realistic locomotion along complex trajectories based on high-level steering control signals. With a visually guided flight task, we demonstrate a neural controller that can use the vision sensors of the body model to control and steer flight. So they basically have sensory inputs, they have this model of the connectome, they have this model of the environment, and they put this all together in this end-to-end reinforcement learning framework. Our project is an open source platform for modeling neural control of sensory motor behavior in an embodied context. So I'm not sure if they have the open source aspect in the article here, but it's open source. I guess it's on GitHub. You can go to the paper and look it up if you're interested. So there's some quotes here. This Janelia group leader, Srinivas Charanga, who's a senior scientist on the project, says the simulation of the body can tell you how commands from the nervous system get translated into actions and behavior. And that how has to do with the shape of the body and the physics of how the body interacts with the world. All of that is codified in the physics simulation. So this is, and so how do you build something like this? Well, the new model builds on previous work to simulate fruit fly behavior, including the Grand Unified Fly, which is a project from the Straw Lab that uses a simplified fly body model and a manual control system to simulate flight. So you don't necessarily need to use a connectome to model flight. You could use something like a control system that you can maybe hand code the parameters of, or you can use something like a Kalman filter as a stand-in for the connectome and produce pretty good results. So you can do something like that. The more recent NeuroMech fly, which I think we talked about in an earlier meeting, uses a realistic body model and a manual control system with learned components to simulate walking. So this is the Grand Unified Fly, which is this project here. This is the Grand Unified Fly model. This is Andrew Straw from the Straw Lab. So this is actually the Dickinson Lab at Caltech. And I know they've been involved in C. elegans simulation as well, but they have this website on the Grand Unified Fly where they kind of talk. I guess it's offline now, but this is a sort of a legacy project, but this is sort of the mirror of that. So what they're doing in this project is they're building a control model. So they're not worried about the connectome per se. They're interested in just building a controller that allows the fly to sort of, control their movements, control the flying movements here. So you have this virtual environment with the fly in it, and you have this controller, and there's this, you have to model the kinematics, the rigid body dynamics, the aerodynamics, the environment with disturbances in the environment, the forces and moments of the aerodynamics that influence the rigid body dynamics, and the sensory systems. And all of this basically creates a state that can then be estimated by the controller, and then when there are errors between the actual desired movement and the output that occurs from all these interactions, then there's this error correction that happens with the controller, and it basically aligns it. So this is a very control theory approach. There's nothing neural about it. It's just good old-fashioned closed loop control, and that's what they've been doing with this. So this actually kind of goes through. This model was from 2008, integrative model of Drosophila flight. So they have a site here, and then also this paper, biologically inspired feedback design for Drosophila flight, and this was at the American Control Conference. And actually, a third paper, an integrative model of insect flight control. So sounds like Morgan had something to say.
Oh, well, it's just it's a really impressive paper. Just digging in some more and seeing the kind of many threads that are being pulled together here. It's just it's really nice. And Mujoko, Todorov's first his original paper was really on these the robots. It was about the action. In this case, it was like legged or hands or whatever, but the action of the robot and the friction, like modeling that is how you make a go from sim to real, right? doing that right is how you do the sim to real, right? And so Mujoko was this physics engine optimized for those for that particular kind of interaction, right? As well as like having all these he was doing some acceleration as well. So super important if you're going to train in sim for the physics engine to be able to run this even faster, right? So then you can have more sim time than clock time, kind of thing. Right? Yeah, it's and then I'm just seeing how they put the geometry together. That's cool. There's I forget who released it, but this week somebody released like 1,400 high-res CT scans of some natural history collection. Anyway, but it's like this would be the kind of data that you could construct these geometry files that you need. But then really interesting what they've added to Mujoko to give it the similar, instead of having the robot leg or hand touching a surface and modeling that interaction, that physics, they're modeling the actual fly at the wing, right?
Yeah.
but a flapping, right? Like it's not flying. So I posted. My son and I went to go see Dune 2.
Oh, okay.
Which was cool. And there was a great video on. I didn't know the evolutionary history of the dragonfly.
Okay.
So it's just kind of interesting. So in bioevolution, there's like a PBS video that's just a little history of the dragonfly.
Yeah.
But you would need you can sort of understand why you would need some changes to the physics engine to better capture that, or unless you're going to be doing the kind of modeling that aircraft manufacturers do. Even then, you'd still want to probably have some changes here, because again, for the loop that they've got in this figure, figure 3. Anyway, it's great, and I see Botnik is also in there. Yeah. So it's got some real deep mind attention.
Yeah.
But interesting that they're not using Flywire AI. Like you said, they don't need any connectome data.
Right.
So there's been someone at the Paris meetup, the NeuroTech Paris meetup, who's been really interested in the Flywire AI data that's available, which everybody knows is like a multi-site storehouse of connectomic data coming from really fine wet lab studies, and anyway, but it's all been kind of collated and made available as one mass download, which is a very different way of tackling this, or different way of looking at this. But I love like what they're doing later on in this is just so cool.
Yeah.
So this would be a great way to get that that kind of craft that they have in Dune actually running in a simulation.
Yeah.
Because it's using a flap.
Oh, okay. Yeah.
Yeah.
Well, you're spoiling the movie, so.
Okay. Well,
yeah.
Hardly the real spoilers. There's a much bigger one at the end.
Okay.
I won't say anymore.
So we have we have Grand Unified Fly, and we have NeuroMech Fly, which of course is this paper, Nature Methods. It's from May of 22. A neuromechanical model of adult Drosophila melanogasters. This is a neuromechanical. It involves the neural mechanisms, but also the mechanics of the body. So, you're looking at sort of these neural network dynamics, musculoskeletal properties in the physical environment. So you have these like surface, interactions when the animal, interacts with surfaces, whether it be the air or a surface that they're walking on. Musculoskeletal properties, what are the muscles doing? What are the joints doing? And then the neural network dynamics, which is like basically the connectome or some stand-in for that. So this talks about, they're kind of understanding the interplay between these elements in their model. So this is where they present NeuroMech Fly, a data-driven model of the widely studied organism Drosophila melanogaster. So they actually, in this model, they combine 4 independent computational modules. So the first is a physics-based simulation environment. So that's like our Mujoko or any other type of physics environment. A biomechanical exoskeleton. So you need to have an embodied model. Three is muscle models and neural network controllers. So you have your muscle models, which are, where you model the muscle as an excitable um, material that is driving movement that gets regulated by the nervous system, and the neural network controllers, which are the inputs to the muscle model. And that, basically we can use a connectome or we can use a control theory model like we saw in the last approach. And so that's where the four, the muscle model, neural network controllers, physics-based simulation, and the exoskeleton. Now, to enable use cases, we must first define the minimum degrees of freedom of the leg from the real three-dimensional kinematic measurements during walking and grooming. So they focus on some specific behaviors of the fruit fly: walking, which is walking on a surface, and then grooming, which is where they're cleaning themselves. And that's a specific set of movements that they can simulate. Then we show how, by replaying these behaviors in the simulator, one can predict otherwise unmeasured torques and contact forces. So you can actually predict some of these forces. You can measure them in the lab as well, and confirm the data in the experimental observation, or the simulation in the experiment. So that's how they're kind of approaching that. They're kind of validating what they get out of the simulation in real world behaviors. Finally, we leverage neuromech fly's full neuromechanical capacity to discover neural networks and muscle parameters that drive locomotor gaits, optimized for speed and stability. So you can use your simulations to predict, once you've validated them with respect to real world observations, you can then make predictions from that. So this increases our understanding of how behaviors emerge from interactions between complex neuromechanical systems and their physical surroundings. So that's neuromech fly. So this is basically the rest of this news article. They talk about, there's another quote here from a machine learning researcher. You take real fly data, how real flies fly and how real flies walk, and train the network to mimic these motions. And then we let this network that we've trained control the fly and tell the fly how to move. It's like a little brain that controls the fly's movement. So again, they're not actually, they're not probing the secrets of the brain. They're just building a simulation that is, pretty impressive. So they talk a little bit about the Mujoko simulator. They had to make upgrades to the simulator, including adhesion actuators that model the forces generated by insect feet gripping a surface. The team was also lucky to have Novati design a new fluid force model. And so this is part of the Mujoko project now, which describes the forces acting on the fly as it moves through the air. So this is the Mujoko simulator. Read the docs, so they have some documentation. This is the introduction. So Mujoko stands for multi-joint dynamics with contact. So this is where you're modeling the joints in the legs and in the wings, and then you have contact forces that you want to model. And this was initially developed by Roboti LLC, and it's actually open sourced. It's been open sourced by DeepMind, and they have the code base available on GitHub. So there's the DeepMind organization, the Mujoko repository, and you can find out a lot there. So this is the Mujoko repository. So if you're interested, you can fork it or take a look at it. And yeah, so you want to say something, Morgan?
I was, I was, and I forgot.
Okay, yeah.
About, oh, sorry, you put back the
This here.
page, not the Mujoko, sorry. It'll come to me. Sorry.
Okay.
I started thinking about Mujoko.
Oh, okay.
And yeah, for a while they let you download it, but it was they didn't. They just let you have the binaries.
Oh, right.
They finally open sourced it a couple of years ago.
So yeah, that's good. Yeah. So I don't know if I wanted to go into the.
Oh, sorry. I
okay.
know what I was going to say. Was the just relates to Josh Bongard's work, and you know, so this is really interesting. It's interesting to see which elements they needed to add to the model, right? So like this is really nice description of what goes into a kind of realistic physics simulation, robotic simulation. Yeah.
Yeah.
So, but then it's like, okay, now, like we were just talking about, can you go sim to real? Right?
Yeah.
And Josh Bongard gave a really funny disembodied heads talk this week.
Oh, really?
I'll try and find the yeah, it was what did they bill it as? It was Josh Bongard presents to 25,000 Chinese students or something like that. But they just had his head talking on top of a virtual dais, you know, like a presentation.
Yeah.
Yeah. It was kind of funny.
So was that to make a point, or was that just the way they?
I think that was just their presentation. You know, yeah, their backdrop for some reason was like, we're just going to take the camera of your head and put it over this thing. It's like, forget your body. I don't know why. So, but he talked a lot about, you know, his evolutionary robotics course. I mean, you know, his work in evolutionary robotics, and you know, this point of like, we simulate these, we do these simulations in sim, you know, and then sometimes it works in the transition to real. You know, so it'd be really interesting. Like what's interesting to me is you've got all these geometry files. You could 3D print everything that they're describing, or you know, that they've really given you, you know, a quite a detailed model of, including the controller. But would you be able to actually make something that flies?
Yeah.
And like, what would the you know, the sim to real points of failure are interesting to discuss too.
Yeah.
You know, and somewhat relates to the, again, this bioevolution video, just talking about that there were dragonflies. I'm making up a number here, but let's say 400 million years ago, that were the size of crows.
Great.
And you know, again, getting to this point about sim to real sim to real, and what works and what doesn't. You know, so you know, how much would the materials matter? You know, again, like how the actual materials matter. You know, so then once you're making it into a real thing, you know, how, yeah, what are the properties of the 3D print that would be important to make that actually fly? You know?
Yeah, there are a lot of interesting, if you think about the evolution of like something like a dragonfly or a fruit fly, you know, that there are a lot of size scaling questions you could ask with, and potentially answer with a simulation. So the idea is that, like in organisms, a lot of times with environment, you get, if it's like an island biogeography or something like that, you get different sizes. So like sometimes if the, you know, an organism is in an island and they don't have any natural predators or competitors, they can grow to very large sizes. And so, or sometimes in evolution, you get certain body plans, certain types of morphologies that scale up or scale down. And then the question is like, you know, can you scale up so much that your flight system doesn't work anymore, or scale down so much that your flight system doesn't work, because when you get down to a certain size, the dynamics of your physical world are different. So, sometimes the fluid dynamics can differ,
Yeah.
or the aerodynamics. And so
Yeah.
those are interesting questions with respect to evolution. Also, what failure modes are there? So we know, like in fruit flies, there are a lot of mutants that we study.
Right.
We could study like if they don't develop a certain part of the wing, or if they, develop a certain motor quirk. What are the consequences of that? So it's interesting to see. You could do things like that in simulation as well.
So I see now that I typed it all in and I hadn't pressed return.
Oh. So what channel is this in?
I put it in bioevolution. Yeah.
Okay, there it is.
Anyway,
in honor of Dune, and that's a YouTube
in honor
video.
of Dune, Anyway, but it's just a nice. I like these videos, and just going over the evolutionary history of dragonflies and being the first. They believe it's the first flying thing.
Oh,
right.
Yeah.
And yeah.
Great.
But really interesting work.
Yeah.
That paper.
Yeah. So we had something in the chat. Sarrah posted, Morgan talking about eye gaze reminded me. I also attended a research symposium last week, and one of the papers presented there was this paper here. It talks about using human eye gaze patterns to detect hallucinations in large language models based on the attentional biases employed by humans when asked to read a passage. And the authors also propose an annotated eye tracking corpus, hallucination gaze corpus. Anyone interested should check it out. So this is the paper here. Eyes show the way, modeling gaze behavior for hallucination detection. That
cool.
looks really good. Yeah,
that's cool. That really reminds me of this Georgia Tech human in the loop reinforcement learning, where they're just really using. I could imagine it in text being so powerful. Where your eye, your eyes plus picking up your look. Oh, that's a mistake. That's a mistake. That's what the Georgia Tech watching Pac-Man.
Oh yeah.
Like the people watching Pac-Man, they could train an agent so much faster if they had the people telling the agent when they were making a mistake. So that's a really interesting one there. Yeah. Check that out.
All right. That's great. So that's all for the simulation, and it's always fascinating to look and see what people are doing in that space. Okay. So let's see. Okay. So we talked about the hackathon. I'll get into this, I think. So in our Cognition Futures group and in our Cybernetics group, we're talking a lot about control, we're talking about information, we're talking about sort of the history of cybernetics and where it's gone and where it's going. And so this is a set of posts, and I don't think we've covered these too much, but this is from Maxim Roginski, who we've talked about a number of times. He's a control theorist and information theorist, and he has these blog posts that I don't think we've gone over, and I'd like to go over them, just kind of frame some of what's going on with, in this area. It has links to what Johann John is talking about, so this is really, I think, interesting to the group in a very broad sense. So this is from 2022, early 2022. I don't think he's written any papers on this or preprints, so correct me if I'm wrong, but if there's some preprints, we can pull them up next time and look at them. This is from his blog, The Information Structuralist, No Information Without Representations. That's interesting. So this is Information and Control in Biology Part 1, Preliminary Considerations. He gives this disclaimer, I'm not a biologist, but have become interested in biology and related matters over the past couple of years. One reason is obviously the pandemic. The other reason is that I think we will not get anywhere interesting in AI unless we understand the concepts of autonomy, self-directedness, integration, and adaptation, and even very simple biological systems. So this is a lot of stuff we're talking about in those groups. This was actually a series of posts that are meant as an extended response to Johann John's old post over at 3 Quarks Daily. And I think this old post here, hopefully it's still live. Okay, so this was the sort of the seed for this. This was 3 Quarks Daily, Johann John. How informative is the concept of biological information? So people have used this idea of biological information. So, you can think of maybe like DNA as containing information and proteins containing information. But you can also think of like what a connectome operates on produces as information, or movement is information. There are all sorts of things that we could say are information, and it's like you can define it as like the Shannon type information, which is of course basis for information theory as we know it in a lot of areas of science, or we can have some other form of information, and we can define it mathematically. But at the end of the day, we should be sort of consistent about what we're talking about. We should be specific, and it has consequences, because you can just say something's information, and that has a magical quality to it. Like, oh, it's information. Okay, well, and you don't know what's really informative in biology, because, quite frankly, we just know that there are patterns that maybe we can capture something as we maybe have a formalization for information. But we don't know if that's important to the biological system itself. So there are a lot of caveats to biological information. We should be very specific, but even when we're specific, we don't want to overinterpret what the role of information is. So this is where kind of Johann John lays out this idea of the different types of information, and then he asks the question, but do we really know what information is in the first place? And is it really a helpful way to think about biological phenomena? I'd like to argue that explanations of natural phenomena that involve information make inappropriate use of our latent, unexamined intuitions about interpersonal communication, blurring the line between what we understand and what we don't quite have a grip on yet. So people, of course, are using a working definition of information. We make these analogies with different types of data that we sort of work with. So, we're of course obviously interested in this computer metaphor, because that's the way humans work with data now. So we have things that are stored on a hard drive or downloaded from the internet. And we have file types and structures of code and things like that. Anything that can be represented in bits and bytes. Vision and hearing are the senses we seem to rely on most often for communication. So it's easy to forget that there are still experiences we cannot really communicate yet, like textures, odors, or tastes. And so, I think Amanda pointed out that, like, first of all, we've had these discussions about sort of the computing metaphor in the brain, and, is the brain a computer and all that. But she's also kind of questioned this notion of memories being this file cabinet phenomena, where, you store your memories in a file cabinet and you go retrieve them and pull them out, and they're pieces of memory that you can quantify. In fact, we'll talk about that next, where you have these units of memory, and all you need to do is go retrieve them, and there they are. So this is, of course, connected to information, because if those things exist, then we should be able to measure their information properties. And so this is the problem with working with information, is that we're using these metaphors that are, may or may not be appropriate to what's actually happening. So this is something that people have kind of applied from electrical engineering. So Shannon information, or the origins of information theory, as Claude Shannon defined it, were really from like telecommunications or electrical engineering. And so we have, it's very well defined for, like, say, looking at noise in a telegraph line or something like that. But that theory may or may not be very applicable to biology. So Claude Shannon was interested in framing information in terms of a transmitter, a channel, and a receiver. So you have something that transmits information, a channel which has a capacity, and then a receiver which picks up the information through that channel. And so, is that the way biology, how information might work in biology? It's a metaphor. So it's an important thing to understand that the structure of information theory as we know it may not be the way biology does it. And in fact, people have borrowed the concept from technological contexts. And so, the other thing about information theory is that signals can be coded as a series of discrete symbols. So this is where people have found sort of a similarity with DNA or even protein sequences or whatever. And you can get these discrete symbols and you can look at the patterns of discrete symbols. But is that really, an appropriate metaphor? Just because they have the common sort of operationalization, does that mean that they're that it's an appropriate method? So he talks about a lot of assumptions we make from information theory, and talks about metaphors and analogies. Now the key question is whether the metaphor of sending and receiving information is particularly helpful when trying to understand biological phenomena. So, parts of information theory require this sort of, the assumptions of information theory to be met. And of course, we have to sort of constrain our analysis accordingly. So can we really, say, for example, take mental phenomena and frame it in this context of a sender and a receiver with a channel that has either perfect information or some type of noise in it? Is that the way to think about mental phenomena? It's it's a good question. And so he talks about it. He goes through a lot of this stuff. He goes through Alan Turing's model of computation and all this other stuff. So it really kind of asks questions about information theory. Now back to this blog post here, part 1. Johann writes, he gives the quote here. Similar sentiments are quoted by Carl Bergstrom and Martin Rosval, and this is in an archive paper, The Transmission Sense of Information. So this is actually on sort of thinking about transmission of information. So this paper was from 2008. Biologists rely heavily on the language of information, coding, and transmission that is commonplace in the field of information theory, as developed by Claude Shannon. But there is open debate about whether such a language is anything more than facile metaphor. Philosophers of biology have argued that when biologists talk about information in genes and evolution, they are not talking about the sort of information that Shannon theory addresses. First, philosophers have suggested that Shannon theory is only used for developing a shallow notion of correlation, the so-called causal sense of information. So, there's this aspect of sort of understanding the correlations at a shallow level. So this is sort of understanding information as a causal phenomenon. Second, they typically argue that in genetics and evolutionary biology, information language is used in a semantic sense. So semantic being a very tricky term in biology, where semantics are deliberately omitted from Shannon theory, and we don't really think about semantics in the same way we think about it in linguistics. They kind of assume that there's a semantic aspect to it, which is actually key to Shannon's theory. What they say here is that neither critique is well-founded. Here we propose an alternative to the causal and semantic senses of information, a transmission sense of information, in which object X conveys information if the function Y is to reduce, by virtue of its sequence properties, uncertainty on the part of the agent which observes X. So it's basically object X has information, function X is to sort of reduce that to some sort of basically like compression, I guess, by virtue of its sequence properties, reduce uncertainty on the part of the agent that observes X. So basically, object X gives less uncertainty to the observer of X, and there's this compression of things in the world that allow that to happen. The transmission sense not only captures much of what biologists intend when they talk about information in genes, but also brings Shannon's theory back to the fore. By taking the viewpoint of a communications engineer and focusing on the decision problem of how information is to be packaged for transport, this approach resolves several problems that have plagued the information concept in biology and highlights a number of important features on the way information is encoded, stored, and transmitted as genetic sequence. So what they're interested in here is genetic sequence. You might have, say, for example, a gene that has information in it that the function of information there is a gene sequence that's transcribed, or it's translated into a protein, and you have sort of the gene sequence can have a lot of different meanings. It can have a lot of different things encoded in it. It produces a lot of transcripts, a lot of protein sequences, etc. But once you get those things transcribed, then you can observe the variations on what the gene is capable of producing. Then you can pick one and you can say that's the information encoded in this gene. So just by looking at the gene, you don't know what the information is. You have to actually see the products of that to see what the actual information is. So that's kind of what they're getting at there. Johann argues that information theory is, on the whole, not an appropriate framework with which to reason about biological information. Carl and Martin, which is that second paper we talked about, argue otherwise, but propose their own framework, what they refer to as the transmission sense of information, which purportedly resolves the issues that trouble a few biologists and many philosophers, in quotes. My goal in this series of posts is to argue that information theory can indeed be applied to biology, but that its proper application needs to be built up from first principles, starting with a serious engagement with its entire conceptual framework. Moreover, I agree with Johann that digital communication is not the right conceptual schema. So, making this into a digital enterprise is maybe not the right way to think about biological information. We should instead be talking about control, programmability, and behaviors. So things like, control, which we saw an example of control theory earlier, being able to regulate things, programmability, which is the ability to sort of, intervene in a program or build a program, and then behaviors that are outputted into the world. I think that's a good sort of summary of this. And so he hits a number of points here of engagement. The first is that operationalization has to come first. So basically, you need to go beyond metaphors and you need to put these things into practice. So information theory always starts with good operational formulation. So you need to have some sort of performance criteria that is not phrased in information theoretic language. So for example, for data compression, we have to think about measures like code length, probability of error, compression ratio, and other things that we can measure in the world and then plug them into our model. So you can't just say that information is about metaphors. You have to have measurable phenomena. So, he gives another example here. So some biologists do emphasize that this paper by Oliver Rivere, this is statistical, well, it's not even showing up. Anyways, this paper by Olivier Rivere talks about this this sort of approach. Bergstrom and Roswell recognize this as well, but in my opinion, do not explore the implications deeply enough. And so, in the context of molecular and evolutionary biology, which is primarily what I'm interested in here, we need to formalize our operational criteria at the level of an organism as the subject and object of evolution. And this is a classic paper by Richard Lewontin called The Organism as Subject, which I think, this is actually, I think, a book chapter, but the organism as the subject and object of evolution. So this is from The Dialectical Biologist by Richard Lewontin, chapter 3. And I guess it was published in a journal originally in 1983. So The Dialectical Biologist is from 1985. So this is a paper that kind of talks about that in more detail. 2, genotypes as behaviors, phenotypes as constrained trajectories. Again, this is where, there's this temptation to look at for information in the genetic code, but what is the genetic code? And so you have to think about sort of what the genotype produces, and then what the phenotype contains. And he gets into some mathematics here, because he is a control theorist after all. And so this kind of goes through some of this. Waddington apparently had an objection to using information theory on the grounds of on the grounds of something called the data processing inequality. So it seems quite obvious to common sense that a rabbit running around in a field contains a much greater amount of variety than a newly fertilized rabbit's egg. How are we to deal with the situation in terms of an information theory whose basic tenet is that information cannot be gained? So there's some, issues with sort of almost relating to the Evergood regulator theorem. They're also very interesting here. Another thing he points out is he points to Robert Rosen's work, which we talked about last time in the paper that we talked about on Thursday. So in order to bring the biology back into the picture, we could follow Robert Rosen's characterization of biological organisms in terms of closure with respect to efficient causation, i.e. the organism's internal ability to maintain certain relations and constraints with its environment, which includes itself. This illustration, I think, provides a correction to the naive picture of the genome computing the organism, just like a Turing machine computing a function, which was criticized by Johann John. And we've talked about that in our cognition futures discussions and in our cybernetics discussions. So I think this is very relevant to some of the things we've been talking about in our meetings and in our approaches there. So the second part of this is where he talks more specifically about the Bergstrom and Roswell transmission sense of information paper. And so in the first post, he outlined the importance of having this proper operational framework. It's also a good idea, however, to pin down even provisionally the kinds of information theoretic quantity one hopes to distill out of the operational formulation. So this is where you want to know what quantity of information you're talking about. And so this is the topic here that he'll focus on. So we talked about this quote here. Biologists think in terms of information at every level of investigation. Signaling pathways transduce information, cells process information, animal signals convey information. Information flows in ecosystems, is encoded in the DNA, is carried by nerve impulses. So information is doing all of these things in different systems. And so you have this diversity of things that it's doing, these functions. Maybe that's not all the same thing. Maybe we need to think about information differently in each context. That's something that you have to consider. In such domains, the utility of the information concept goes unchallenged. So, we don't really have a way to sort of characterize even what information is doing or is functional in terms of. So if I say that, some system has a certain amount of information, I could say, okay, what is it doing in the system? What's the effect? And that's something you have to define and kind of make explicit. when a brain scientist says that nerves transmit information, nobody balks. I don't know about nobody, but but when geneticists or evolutionary biologists use information language in their day-to-day work, a few biologists and many philosophers become anxious about whether this language can be justified as anything more than a facile metaphor. So, I mean, this is the idea that you don't want to sort of overinterpret or use it as a sort of, evidence of spurious correlations or other things. So, while this recognition of the importance of operationalization is not common in biology, I think that still misses an important point. The relevant decision problem is not that of a communications engineer. It is that of a control engineer, whose primary aim is to ensure reliable transmission of the global constraints governing the unfolding of phenotypes, starting with development and continuing on through the organism's lifetime. In other words, the meaning and use, or the semantics and the pragmatics of the genome are primary. The symbolic packaging or the syntax is secondary. So in other words, the sequence is not the important thing. It's what the sequence produces in different environmental contexts, in different transcriptional contexts and the like. This is something I guess he's going to follow up on in future posts. So he gives a model and kind of goes through the mathematics of it, talking about the temporal evolution of genotypes and phenotypes in a random environment. Then the genotype and environment are modeled using two discrete time stochastic processes. Notice that the environment is not necessarily Markovian, but the genome process is a Markov process in a random environment. So it means that Markovian just basically means that it's a set of discrete states that are random. You can think of environment that way, but it doesn't have to be. There can be structure in the environment. This is a very simple model of asexual reproduction, and the process distribution of GT models mutations through stochastic dependence over time and selection. At this point, I hope I've convinced you that we need to look at directed rather than mutual information. So there are different types of information, theoretic information, that we need to look at the right type. Now, however, we will work with directed information between processes. So we're using this process aspect, which of course we talked about as being different things in different systems. And it gives the math for that. So focusing on the temporal unfolding of genes, proteins, and environments do not rid us of the parity thesis, since both genes and environments affect the phenotype. From the viewpoints of a communications engineer, this equation does indeed describe a communication channel. The environment, ET, is a fixed noise process that plays some part in the evolution of GT. At each time t, the current output genome, GT, is determined stochastically by the previous input genome and by environmental noise. So you have a genomic state, a noise state. You combine them into the next state, and you move on. So it's very, basic modeling, but it's important to tease all this out. These are things that we can think about in terms of what we talk about in our Cognition Futures group and our cybernetics group. And I think it has a lot of relevance, especially what we think about when we talk about cybernetics, of biology and of maybe like neuroscience as well.
Yeah, for sure. Again, I would point out the Dennis Noble, Richard Dawkins discussion that I posted again on bioevolution, and then again some of Michael Levin's thoughts about how the necessity for kind of redescription of terms to accompany his ideas on morphogenesis in particular, which I think is one of those, like protein folding sequences and their kind of structure, and like what is evolution operating on.
Yeah.
Like that's a, to some degree, that's actually a simple case in comparison to the morphogenesis and regeneration well, the morphogenesis in particular.
Yeah.
Thoughts and just tissue, complex tissue, and his ideas on just like what is the information in DNA actually encoding about that?
Yeah.
If anything. Anyway, it's a really interesting discussion.
Yeah. I think one thing I got from this set of blog posts is that there's this heterogeneity of information. So it's like you talk about like one measure of information, and then you have all these functions that you could apply it to. Is it like how can you say that that's like a unified theory of biological? Basically, you're saying it's a unified theory of biological function. How can you justify that? Can you say that like neural transmission, for example, is the same as something like transcription? When you put it like that, it doesn't sound reasonable, maybe. But if you talk about it in terms of information or very general terms, then maybe it sounds more reasonable. And so,
well, I mean, I think that's somewhat. I mean, Levin was definitely trying to make we need to think about processes as opposed to what would be the opposite? What would be the old idea?
Well, I guess like different types of. I mean, thinking as a process is having this sort of things happen, and usually in biology we think about like facts. I don't want to say stamp collecting, but you have usually like you identify key genes, and they say that these are involved in this, and you don't plug it into a process necessarily.
That's
Although
right.
in some areas of biology, you have to think about a process. So like you might have like a study where you look at a gene expressed in a tissue and you have markers, and you say if those markers are present or absent, and versus like having a model of like a network or like some sort of like metabolic pathway, and then filling in the details and then modeling how that works, and then saying, okay, the parts are there, but then they work in a certain way and they give an output. And that output isn't necessarily the sum of the parts. It's all these different conditional things that are going on, etc. So that's I guess the difference between process and like sort of the detail-oriented studies that we have a lot of, where we say identify things basically.
Yeah, it's these are old discussions that again, I mean I point out the Dawkins just mainly because I think it's nice to have someone like Dennis Noble keeping that, you in a sense you need to actively be attacking that kind of orthodox genetic information is clear cut.
Yeah.
Like all the time, I think partly just because it's so it's easy to fall into. And so it is unfortunate that I don't know if he's got it does seem like, I mean, this is the criticism of some of the other, would they be called the Evo-Devo folks? But
there's like an extended synthesis group.
Extended synthesis.
They do a lot of different approaches.
It's extended synthesis is what, and is that they've got a set of stamps in a sense of edge cases, as opposed to a kind of a new paradigm for us to that we could memorize and then regurgitate, because it does
That's interesting. You talk about a set of edge cases and differentiating that from a paradigm. I think it's interesting because a lot of times, when we theory build, we're building like from example. I mean, we build these models, but you have to have examples in place, and so like Darwin didn't come upon evolution just kind of spontaneously. There's a lot of stuff going on before.
Right, and he wasn't the only one.
Right.
Right? I mean, there was obviously enough cases, enough in the air that somebody in parallel could be doing the same. And Jesse's not here, but it just makes me think of philosophy of science and especially of the kind of Kuhnian revolutions, in terms of like these edge cases build up, like in physics and black body radiation and things like that, where it's these become the nuggets of the new theory, but at the time they seem like unexplained or paradoxical or
Okay. So I don't know if Amanda had anything she wanted to add.
No, nothing to add, but this has been a great conversation.
Okay, thank you. Yeah. It looks like Jesse had to leave and Sarah had to leave, so thank you for attending. Okay, I'm going to talk about, I promised this. Now, in the last discussion, we talked about sort of the assumptions of kind of like maybe like memory, and where we have, actually, I think I talked about that in the Drosophila stuff as well. And, the idea that we had like pieces of memory that were sort of defined as like the memory, the nugget or kernel of a memory, that we could, identify that and say, okay, this is a memory. We can, erase it or enhance it or whatever. And so, that's the idea. And then, of course, you might question, okay, do we even have that sort of a system? And of course, so there's been sort of a move, sort of a goal, or like a holy grail in psychology to find this sort of thing, this unit of memory. And there, like I think I've mentioned before, there are a lot of lesioning experiments that people have done, especially in the medial temporal lobe, where they can lesion parts of it, and you can have things like amnesia. You can have disruption of memory encoding. You can also disrupt memory retrieval and encoding with chemical interventions. So you can modify proteins. You can introduce certain chemicals into model. I think they've done this in the mouse brain or rat brain, where they can disrupt memories. But that still doesn't say that it's like a unit of information. You're just disrupting it in some way that's anatomically specific. So whether those memories exist in some sort of network where they're put together, or whether there's a unit of information that contains a memory, we still don't know. So that leads us to this quest for the engram. Morgan is kind of shaking his head knowingly. But so the idea is that, the engram exists as this sort of idealization of a unit of memory. So this is a paper from Science in 2020. This is a review paper on memory engrams, recalling the past and imagining the future. And so this goes back to, I guess, ancient times. So the idea that memory is stored as enduring changes in the brain dates back at least to the time of Plato and Aristotle, but its scientific articulation emerged in the 20th century, which Richard Semon introduced the term engram to describe the neural substrate for storing and recalling memory. So this is where they kind of come up with this term, and it has a very long history. But this idea of, okay, what is a memory? Is it a discrete thing, or is it just something that emerges from the anatomy? And this was before any of these lesion studies, really, I guess, or maybe concurrent to them. They came up with this term engram, which is where you could find a unit of memory in the brain. And if you remember the movie Total Recall, the engram, I think, implicitly plays a very large role in what they're doing. They're trying to modify, erase, and change memories, and they have this what is it, the Recall Institute, where they modify your memories. It's based on a science fiction novel, so they've worked it all out in the novel. But anyways, this idea of engram has been around a while, and this is basically what they've been chasing for quite a while in psychology. So in Simon's formulation, he proposed that an experience activates a population of neurons that undergo persistent chemical and or physical changes to become an engram. So it's like some part of the brain, some population of neurons, they have to undergo some sort of modification to become a discrete engram that then retains that memory. So everything about the memory, we don't know, like if it's parts of a larger memory or whatever, that's the part of the brain that does that. So you can localize it to a very specific place. Now, this is interesting because you can make a couple of comments about this. One is that, we know from like the work on long-term potentiation that there are certain areas, that there are mechanisms at the synaptic level that enhance, memory, that enhance the association between neurons. So we can think of the engram that way as sort of the enhanced association between neurons. And we think of Hebbian learning, that's certainly what that's describing is the reinforcement of different relationships between different neurons. But you can also think about this as sort of, people have proposed things like grandmother cells, where they're responsive to a certain specific face, like the face of your grandmother. And so one might say, okay, well, you have neurons or you have groups of neurons that respond to specific stimuli. They respond to maybe like every object that you observe. They might respond to specific faces and so forth. And so if you think about this in terms of discrete parts of the anatomy, you realize that if you had separable parts of the anatomy for everything you remember, you don't probably have enough brain territory to encode all of that. So they have to probably overlap. Maybe they encode certain features of things, but not others. And there's a whole literature on like face perception and object perception that sort of get into the details of that. But that's not what we're talking about today. But it is important to understand this idea of the engram, because you have to define what an engram actually encodes. So this is something that Simon proposed, and then subsequent reactivation of the engram by cues available at the time of experience induces memory retrieval. So you reactivate the engram. The engram is there, it's latent, it needs to be reactivated by something at the time of experience. So that's the model. Then after Carl Lashley failed to find the engram in a rat brain, so Lashley tested this hypothesis and it failed. They couldn't find it. Studies attempting to localize an engram were largely abandoned. So Lashley's work was really kind of where that fell by the wayside. Spurred by Donald O. Hebb's theory that augmented synaptic strength and neuronal connectivity are critical for memory formation, and this is Hebbian learning as defined in terms of the synaptic reinforcement of the relationship between different neurons. Many researchers showed that enhanced synaptic strength was correlated with memory. So Hebbian learning is where you're exposed to a stimulus, you learn, those connections are reinforced, and then that is retained over time, and you can retrieve it with cues, but it still doesn't really point to an engram. It's just kind of an anatomical description of memory, and finding an actual engram is extremely hard. Nonetheless, the causal relationship between these enduring changes in synaptic connectivity with a specific behavioral identifiable memory at the level of the cell ensemble, which is the way they kind of describe an engram, awaited further advances in experimental technologies. So this review kind of goes through the history here. There's an outlook here, which is the ability to identify and manipulate engram cells and brain-wide engram complexes has introduced an exciting new area of memory research. So now people are kind of revisiting this concept. They're looking at how to maybe manipulate engram cells or look for engram complexes brain-wide. So they're looking more at the network aspect of it. The findings from many labs are beginning to define an engram as the basic unit of memory. So this is basically, people are kind of using this term to think of the basic unit of memory. And so there are a number of findings in this paper that kind of lay out that field of research. However, many questions remain. In the short term, it is critical to characterize how information is stored in an engram. So again, we go back to this idea of information and what it is and defining it, and how, of course, it has to store, the engram has to store something. What is it? Is it Shannon information, or is it like, just synaptic connections, like, in neural networks we have weights, or is it something else? Including how engram architecture affects memory quality, strength, and precision. So engram architecture, or the connections between the cells in an engram, can affect all these things. Also, how multiple engrams interact in networks, how engrams change over time, and the role of engram silencing these processes. So engrams can be silenced. So, when you think about retrieval of memories, not all engrams are going to be represented in that retrieval. There might be a network of engrams, and those engrams can be silenced or enhanced accordingly. So that brings up a lot of interesting points. Number one is that the original idea of the engram was kind of not oriented in terms of anatomical specificity. What I mean by that is that there was this idea that there was part of the brain that did something, and there's this whole history in psychology of different parts of the brain doing some high-end functional thing, and so that's not what we're talking about. We're talking about just now we're talking about specific anatomical functions and localizing those. And so you might look at an fMRI image and see a bunch of splotches across the brain associated with retrieving a certain memory. And so then we can characterize those as engrams and build a network perhaps to describe their activation. And of course, we don't know necessarily if we encode every memory task equally, or if we can reuse engrams for different things or what. So that's still kind of an outstanding question. The long-term goal of engram research is to leverage the fundamental findings for rodent engram studies to understand how information is acquired, stored, and used, and facilitate the treatment of memory or other information processing disorders. The second paper is Finding the Engram, which is this review. I think it's one of the authors the same as the other paper. And this paper kind of, it's one of these, I think, Nature reviews. So they have definitions on the side here. They talk about neuronal ensembles, for example, and they define terms, so that's good. And in this review, the abstract reads, many attempts have been made to localize the physical trace of a memory or engram in the brain. However, until recently, engrams have remained largely elusive. In this review, we developed 4 defining criterion that enable us to critically assess the recent progress that has been made towards finding the engram. So they define 4 criterion. Recent capture studies use novel approaches to tag population of neurons that are active during memory encoding. So they use these capture studies, which are methodological technique that allow them to tag populations of neurons. And so they can look at this physiologically and see what is going on during memory encoding, and thereby allowing these engram-associated neurons to be manipulated at later times. So you can look at the actual cells involved or the regions involved in these things, and then look at, do manipulation studies later to see if those things are reactivated. So you have to identify what neurons you're talking about and then see if they're reactivated later. That's very different than looking at a bunch of splotches in an fMRI image and then just saying, well, those are engrams, because they may not be engrams. They may be just cells that are encoding things, and the encoding might change over time to different neurons. But we don't really know. That's sort of one of the challenges of engram studies, I guess. We propose that findings from the capture studies represent considerable progress in allowing us to observe, erase, and express the engram. this is a lifetime diagram showing the lifetime of the engram, going from encoding, which is where, so the y-axis is the engram state. It can either be active or dormant. And then you have time. So you have this consolidation phase where the organism is learning something, it's consolidating the memory, it's being put together. They're encoded in some set of neurons, this network of neurons, this neuronal ensemble, as they say. And the neuron active state varies from high activation to low activation. So you can see that a memory is encoded in a neuronal ensemble with a different, neurons of different specificity, high activity, low activity. And then this goes over time. This gets preserved as it's consolidated, and the engram state becomes dormant as it's consolidated and it's not recalled. Then upon retrieval, it goes back to an active state and then returns to an inactive state as it's reconsolidated. So every memory gets recalled, it's retrieved, and then it's reconsolidated. So sometimes when you retrieve a memory, it might change because you remember new details about it, or so this neuronal ensemble, this encoding is not perfect. It could be imperfect. It could be incomplete, and so you can change it. You can forget things. You can add things later as it's retrieved, as you remember things, and then it's reconsolidated as a memory, and then it's retrieved again and reconsolidated, and so forth. So that's their model of the engram. They have some nice figures here where they show in cortex the different layers, what's going on, in dentate gyrus and in the amygdala. So they look at different brain regions. They look at storage, retrieval. So in storage, things are dormant. In retrieval, you get more activation. And then they show this in the context of associative learning. And then they can actually do things with optogenetics to stimulate different neurons and tag them and measure their activity with respect to the engram. This is a different set of authors, and this is the emergent engram, historical legacy and contemporary discovery. So this is where they talk about technological advances that have made it possible to capture a specific assembly of neurons active during a learning event. And so you can also manipulate the captured cells with, like we saw in the last paper with optogenetics, demonstrating some form of relationship between brief retention events and the cell assembly. The reductionist claim of localizing the engram has been met with considerable skepticism. So the engram is really a reductionist enterprise, the idea that you can reduce memory to like these set of cells or a single cell or whatever. And so people have been skeptical of that. And of course, it has a iffy history because we've failed at least once. The potential for off-target effects in cell capture techniques, such as optogenetics, which we talked about in the last paper, reveal serious limitations when given the highly interconnected nature of brain networks beyond a selective assembly of cells in a restricted area of manipulation. So what they're saying is that, you have these techniques that we can use that kind of you might think this is really the path forward. But actually it reveals serious limitations of, this engram hypothesis, given how brain networks are highly interconnected. They go beyond selective assemblies of cells. And so we're only really manipulating a small subset of that network. And so we can't really make huge assumptions about the totality of memories given just the ability to probe small areas of the brain. Recent studies of subcortical-cortical interactions, which are the neocortex, of course, we saw with the layers, and then the subcortical areas, such as the dentate gyrus and the amygdala, and more generally, the medial temporal lobe. So there are these interactions between the subcortical structures and the cortex, and that's how memory is retrieved. You're going from the medial temporal lobe to the cortex and back and forth. And, so there are a number of different regions of the brain where memories are encoded and retrieved from. So there's this whole area, a separate area of subcortical-cortical interactions, and people looking at that. And so this prompted them to review the historic search for the engram. And this reveals a parallel between the empirical attempts to localize the engram in cortical, then subcortical systems. So there's this, they've been trying to localize the engram in both of these areas. And, I guess there's a different history depending on which area you're looking at. When brought together conceptually, the very extensive independent work of Carl Ashley and Robert Thompson suggests that each held a piece of the puzzle. Recent research implicates the interaction between subcortical memory systems and association cortex, which is the neocortex, and the transformation in mnemonic information from a short-term process of plasticity to a long-term state of stability. So basically, you have to look at these interactions between neocortex and things like the medial temporal lobe and other areas. And this looking at both of these gives you the information you need to see this sort of transformation from short-term plasticity to long-term stability. We propose that one function of subcortical-cortical connectivity is to continuously update contextually retrieved long-term memory during reconsolidation of newly acquired information processing, creating a constantly evolving emergent engram. So basically what they're saying here is that you need to, like what we saw with that image, with that figure in the last paper, or I guess in the first paper, is that, of course, the neuronal ensemble is encoded with information, it becomes dormant, then it's retrieved, and it's reconsolidated. But that image made it look like it was all just sort of this static process in terms of the network. What they're actually talking about is that the engram is constantly changing. It's not just that it's, there obviously memory needs to have the quality of preservation, of durability. So the memory must persist. Otherwise, it wouldn't be a memory. But, you also have to incorporate newly acquired information. So oftentimes you build upon previous memories. You might build context around that memory, or you might have other memories that interact with it. You might have, you might update that memory, you might lose that memory, but you also might gain expertise or some other memory that helps you put the pieces together. So there are a lot of things here that you have to think about in terms of if you're going to propose an engram or a unit of memory, you also have to propose a lot of things, other mechanisms that allow you to use those memories. And so there were two routes of investigation historically. The first route was by Hebb, who described cell assemblies and the learning rule as an enduring synaptic change, later supported by the discovery of long-term potentiation. So Hebb in 1949 discovered Hebbian learning, and then long-term potentiation was actually a bit later with Bliss and Lomo and Bliss and Collinridge, and those were in the 70s through the 90s. So they were doing this work on long-term potentiation, which is where Hebbian learning is basically preserved over long time periods. So this is one aspect of engram research. The second route, taken by Hebb's mentor Carl Ashley, that work was done in the 1950s, is set out to localize an engram empirically, somewhere within the association cortex or the neocortex, thought to be the repository of long-term memory. So there are a number of papers on this. Carl Ashley used these sort of behavioral techniques, post-training lesion techniques, to disrupt the retrieval of memory in rats and monkeys. After decades of systematic empirical work, Ashley concluded that it was not possible to localize an engram in association cortex, an important distinction, because memory was widely distributed throughout a network of neurons that all had equal potential to contribute to the memory trace. So Ashley did all this work, and he said, well, it's in the network. Sorry. Robert Thompson continued Ashley's work in subcortical structures using pre- and post-training lesions. Though this work has not been widely recognized in recent reviews of the engram, it has been pointed out that Thompson was friends with Carl Ashley at Yerke's Primate Center, where they discussed research and the lack of progress in localizing an engram. So basically, they did talk to one another, but they didn't. I guess they weren't, agreeing on what was going on. Robert Thompson thought that Lashley may not be looking in the right place for engrams, and his interest in Penfield's centroencephalic integrating system as the general learning system resulted in this continuation of a systematic empirical search within subcortical structures, resulting in greater success than Lashley's work. So they didn't really see eye to eye on where these structures were. So that was maybe one of the problems here. So this kind of goes through Thompson's work and more success, and then this kind of led into the modern research where people are trying to put together these pieces. But I think really what needed to happen was more technological advancement so we could get better recording from the brain, better specificity of what's going on in the brain and so forth.
Yeah, I would say, I mean, the recordings definitely, I think it's also the tasks.
Yeah, well, yeah.
I mean, I don't know. I guess that maybe that sounds obvious, but just in the sense that, part of what distinguished them was the different tasks and the kind of the evidence from those that had this, had these different features that, anyway, it's I'm just looking at the review article, the R.J. McDonald's 2013 triple dissociation of memory systems, and he's using that 8-arm radial maze, and like you said, it's all about when you're lesioning and what you're what aspects of the task you're considering important. But just also, this is one of the tasks that is implemented in the neurorobotics platform.
Okay.
Like you could, just thinking about actually bringing this back to, simulations and,
Right.
and yeah. But it's also really interesting to cover all these papers because, again, it was such a, such a pleasure to talk with Carl Pribram and him being like, well, when I was talking with Penfield or last year, it's like he knew all these guys too. Yeah. So
Great.
it's definitely worth. I've said this before, but it's worth reading his autobiography just because he's got so many crazy stories to tell about all these same people. And he ran the Yerkes for a while too.
Oh yeah.
Anyway, so Jesse had something he wanted to.
Yeah, he said one thing I'd like to mention before we break about practice-based research and some interest in looking more at this sort of education manner type stuff. Yeah, that definitely we should get back to that. And I know that we met with last Friday. We met with Jen, and I think she's done some good work. And so we'll keep following up on that, and let's make that a priority this summer as well.
Yeah, just as a two very, very, very brief thing to say about it. It actually came up through plot twisters, and I foresee plot twisters is really deep into. I really just found out what the term means or is in practice. I'm still learning about what it means and the nuances of it. But I'm seeing something. There's some interest there to do some things that I think fit plot twisters and some aspects of JoPro. And I also think it might be nice to look at almost like what the lab has tried to do in terms of practice-based research. I think also a really specific example of this would be a lot of the ethos and method, why the Society Ethics Tech team happened, in the sense of one of the reasons I wanted to do it was to make a space for people with very obviously different backgrounds to come together and talk about stuff.
or at least be on the same stage with somebody else, even if you're both early career folks who were, in different spaces interfacing with technology. Like that's sort of an obvious example, but I think much of the lab itself and how Bradley set it up, the vision, the way it's distributed, all that stuff kind of fits with that. And I think there's something to essentially to put together, like maybe a publication, sure, but there's something to kind of put specifically about that. And I'm mentioning that just because there's going to be some inertia on that from Plot Twisters and maybe Joe Pro also. And I think there's something here too. So quick plug for that. I need to, it's sort of a late breaking thing because I've just realized there's sort of a vein of stuff here that should be mined. But what about that next time? I know I missed a bunch of things earlier. If there's something really critical, let me know in Slack, but otherwise I'll try to review the meeting later. But thank you for everything else. I'll be working on my embodied intelligence stuff and everything else.
That's great.
For next week.
Thanks.
Thanks,
All right.
everybody.
I think that's it for today. Thanks for attending. Talk to you later.
Bye-bye.
Bye.
Yep, talk to you soon.
Talk to you soon.
Take care.
Take care. Bye.